Okay, you guys, this is for whoever's watching this video, sorry about that. Somehow I paused it, but I'm not going to start all over. So anyway, we we pick up here. We found the exponential regression, and so well, we're going to do some more work, but that's really the question that comes up at number 5. So I'm going to move down to number 5 here, and yeah, so let's move to number 5. Number 5 says to use the data from exercise 1. If you look at this, number 5, right at the bottom, it says use the data from exercise 1. Enter the data into the two lists. We did that. Okay, use the exponential regression feature and write the constants A and B. Now, what was the R value that we came up with? 0.94. So that looks pretty high. We came up with A equal to 3.21 and B was equal to 2. So the equation that we would write looks like this. Y equals 3.21 times 2 to the x. Okay, that's what the equation looks like. Now, it's not enough to just write the equation. What we would like to do is graph it and see how well it actually fits the data. It says R is equal to 0.94, so we would assume that it probably fits it pretty well. Let's check to see if that works out. Again, you can see R is 0.94. Here you have A and B. And for people that are watching, we will do this again so you can see how it actually works. So if I quit this and I go into Y equals, and I type in 3.21 times 2 to the x, it's neat because everybody has seemed kind of interested that it fits the data so well, just like Summer said. If you look at this graph, watch the graph. It does a very good job of going through those points. Now, what's that? Nathan brings up a good point. He says it just goes through one of them, okay? The fact is this. There does exist a polynomial that we could figure out that models that data 100% accurately, but it's an extremely difficult polynomial to work with. This does a really good job of modeling it very closely, and this is an easy function to work with, and we'll show you more about that later. Here's what I want you guys to do right now, okay? Well, actually, we'll do this together and we'll go to the back side. Okay, let's check to see if this data represents something that is exponential as well. I look at the top differences. What's the difference in the x values each time? 1, 1, 1, 1. So that works out. Let's look at the difference in the y values. What's the difference between 4/5 and 1? What's the difference between 1 and 2? And 5, then 25. So, yes. So Taylor sees that the ratio that exists between each one is 5. And the way that she would figure that out is she would say 25 over 5 and 5 over 1 and 1 over 1/5. Those are all the same thing. So if she actually checked that by hand, it would work out. Now, you guys, I want to make something clear. So far, we've come up with examples where there is the same ratio every time. If the ratio is close, like let's say it's say 5.1 or 4.9 or something very close to it every time, we would say that probably represents something that's exponential. Okay. We try the next one. How much does this go up by? 1/6 to 1. 5 over 6. Okay. How about 1 to 6? 6 to 12. 12 to 18. Does this data represent something that's exponential? No, it doesn't. In fact, it might represent something that's more linear. The reason why I say that is because it goes up by about 5 or 6 each time. I don't know what's going on with this 5, 6 at the beginning, but you know, if we were to try to model that, we would have to look at something else. Maybe it's logarithmic. All right. Okay, flip over the next sheet. Yep, back of that sheet. And we're going to do a couple more examples, and then we'll be done for the day. But we want to try the same type of process. I'll work through one with you, then I want you to try 2, 3, and 4 on your own. Problem 1 says, determine whether f is an exponential function of x. If so, find the constant ratio. First of all, let's determine if we really go up by a consistent constant number. What do we go up by each time in number 1? We go up by 1 each time. But for our outputs, it looks like we go down 6, so I'm going to write negative 6. And we go down 2, so negative 2, negative 0.7, and then up 0.6. So if you were to divide these off, say 0.6 over negative 0.7, and negative 0.7 over negative 2, and negative 2 over negative 6, are those going to be the same? No, they're not. So this is not exponential. I want you to try that for 2, 3, and 4. We are not going to do 5 and 6. You guys know how to plug stuff into your calculator now. But we are going to do example 7, and example 7 works out pretty neat. So try 2, 3, and 4. I'll pause the video. And again, you have to find the first differences. So I'll do the example. What's the difference between 0.03 and 0.01? 0.02, then 0.15 and 0.03, 0.12. Then 0.15 to 0.87 would be 0.72, and then 0.519 to 0.87, 0.4 or 4 point what? What'd you get, Alex? 4 point what? 32. So if you would take these and divide, the next one by the previous one, you do come up with 6. Okay. Well, even if you had 13, it should have been pretty close, I'm guessing. Yeah, so we would still say that's exponential. In this case, yes, the ratio is 3. In this case, no, there is not a ratio that really exists. Number 3. Okay. All right. So the first thing you should be able to do is determine if it's exponential or not. Okay. Now that we've determined that they're exponential, let's try a word problem. We'll end with this today. It says Bernice is selling seashells. It could be, I guess, Sally sells seashells by the seashore. Bernice is selling seashells. She is found at the beach. The price of each shell depends on its length. Find an exponential model for the data. So first of all, Alex, if we want to find whether or not it's exponential, just because I heard you talking, so phenomenal. So as we look at this data right here, does it go up by a consistent amount each time? No. So because it does not go up by a consistent amount, it's hard to just look at the data. So I have to plot it to see whether or not it really looks exponential. So let's take out our calculator. They tell us it's exponential, but let's verify it, all right? We'll go into into our list. So if I go stat and enter on edit, I'm going to clear, enter to get rid of my lists. And I'm going to type in my new data points. Well, they say that the data is exponential. We're going to use it to solve some equations. We're going to actually get use regression to come up with a model. I'm going to type in the data to just make sure that it is exponential. Okay. Let me try to put this in context for you guys real quick. A lot of times when we sell products, it really follows a linear model. For example, if I go to the store and I can get 1 can of Mountain Dew for 25 cents, what do you think I would pay to get a 24 pack? About, what's 1/4 of 24? 6. I would pay about $6. Okay. So think of it the other way. What if it costs 25 cents to buy a can of Mountain Dew at the stores, or to buy a 24 pack, it cost $100? When you went to the store, what would you just do? Buy 24 individual cans, and you pay the $6. So why is this different in this problem? If you look at this data, if Bernice is going to sell a, say, 20 centimeter shell, it's going to cost a lot of money, as opposed to, I mean, a ridiculous amount of money, as opposed to if she sold a small seashell. Why wouldn't somebody just, let's say a 4-inch or 4 centimeter seashell costs a couple bucks. Why not just buy a bunch of those? Okay, because you can't just piece them together and come up with that same value. The fact is that a large seashell is very rare, and so that's why the price jumps up so much. So as you look at this data, if we look at the window and we go from 0 to, we'll say, 40, and then we go from, say, 0 to 50, and if I graph this data, whoop, yep. Look at my data. Does that look exponential? It sure does. And as you can see, the larger shell that you buy, the more it's going to cost, and it's going to go up in a very very quick manner. For example, if I go to the store and I go to buy a 1/4 carat diamond, I could get that at a reasonable price. But if you double the size, you more than double the price. And if you quadruple the size, you more than quadruple the price. It continues to go up at an exponential rate. So, another one. So, let's actually figure out the equation behind this. If we go to stat and calculate, again, if you go all the way down, you'll find exponential regression, or 0. Press enter, and sure enough, you come up with an R value of 0.998. So I'm going to write that down. R equals 0.998. And we come up with an equation that looks as follows. It says A is 0.965. So Y equals 0.965 times, what is it, 1.16 to the x power. So that's an equation that represents my data. Let's see how well it represents the data. As you go into Y equals and you type in 0.965 times 1.16 to the x, we get, look at that. It fits it nearly perfectly. And so we would say that this is a really, really good model, that it represents it very accurately. In fact, we would say it's a very good prediction model as well. So let's make use of this in the final part of our problem. As you notice, the problem says, what is the length of a shell selling for $9? So I need to do some solving here. I'm going to rewrite my equation so I can understand it. Y represents the price, and Y is the price and X is the length. So I'm going to say dollars is equal to 0.965 times 1.16 to the length. So that's my equation, and it says, what is the length of a shell selling for $9? How would I solve that? Okay, so I plug in 9, so 9 is equal to 0.965 times 1.16 to the x power. Divide both sides by 9. 9 divided by 0.965 is 9.33 about. So 9.33 is equal to 1.16 to the x. How do I solve for the x? What? Log base. Yep, that's why we learned everything we did this past unit. The way we get rid of that exponent is we take the log base 1.16 of both sides. You end up with the log of 9.33 over the log of 1.16 when you use your change of base formula, and you get x, I believe, is approximately 15.04, something like that. Done. So it's approximately $15.04. Do you pass? Okay, I'm sorry, you guys. It's not dollars, it's length. So it's 15.04 centimeters would be the approximate size that should sell for $9. So if I want to do this last part here, I have, we said if Bernice had, or what is the length of a shell selling for $9? We said about 15 centimeters. If I want to do the other part, if Bernice found a 40 centimeter conch shell, how much should she sell it for? We would take that 40 and plug it in for L. Now, you can either do that by hand, or remember, the other day I showed you guys on your calculator, there's a couple ways to do this. As you look at the graph, we can either go second calculate, enter your value, and as long as 40 is in your window, second trace, it will give me 365.46, or question? Yep, value. Or you could go to table, second table, and if you type in 40, as you can see, you get 365.47. So either way you can figure it out, 65.47. It's a nice feature that allows you to do. So that's all I have for you guys today. And be ready for homework on Monday and Tuesday next week.